All right, welcome to the lesson today, talking about 15.7 triple integrals. And in order to do triple integrals, we used to find the region in between two curves, and that helped us define our region. And what a double integral will allow us to do was that we were able to find. Well, there's really two things that a double integral helped us find. We were able to find the area underneath the curve. The area underneath the surface, or we were able to find the mass of a piece of lamina. And if you remember, lamina is that really, really thin strip, like I said, not a strip, but like a really thin, very thin, plate. It's got two dimensions. It's got length, it's got width, but it's very, 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 very thin. And it helped us find the mass of that. Now, for a triple integral, we really, we thinking about extending, we used to say area under a curve for single integral, volume underneath, a surface for double integral. Well, what about, and that's three dimensions, we go off again in triple integrals, and now we're talking about a four-dimensional object, and we're finding some unit of measurement for this four-dimensional object. All right. Again, that you aren't going to be able to really see the concept of, and so that's kind of why we talked about lamina a section or two sections ago, because what a triple integral allows us to do is it allows us to find the mass of a three-dimensional object. So now we're extending that, instead of now having that two-dimensional lamina, we're adding thickness to it, and that's our 3D object, and we're able to find the mass of a 3D object, as long as the function inside of our integral is the mass density function. All right, we're able to find the mass of that. So that's, the main application when we're talking about three-dimensional objects. It also allows us to kind of find the volume of, a shape that, we're first going to define the region as an integral, and so instead of having to rotate about it, we also are able to find the volume, but we'll talk about that in the next section. But again, so same rules apply, to find the integral. We're just going to add up all these, cubes that are inside of our, whatever, our object is. That's how we're going to find the triple integral. And so again, we can find that, setting it up the same way. Now again, a lot of the same rules apply for double and triple integrals. We have Fubini's theorem. Again, Fubini's theorem is the order is not going to matter of integration as long as the integrals, match up with, what you're taking it with respect to. And so there's actually going to, so you have like three permutations, and so 3 factorial, and that's going to give us 6. So we have 6 different types of possible orders that we're going to have. And so I wrote them down here instead of having for you to watch the video of me writing them all down. I defined these, all the integrals by t instead of having to say RS, CD, BA, like our regions. I just went ahead and put all of our regions as t to represent, we have a triple integral. And again, I just changed, the order of all these. All right, so instead of starting off with dx, dy, dz, I chose dx, dz, dy. And I just changed the order so that you could see the orders, can change based off of Fubini's theorem for triple integrals. All right, so now what we're going to do is we're going to evaluate the integral in the triple integral xy plus z squared. But we're going to try to do this 3 different ways. And it's nice because the region is not defined by any variables, just by, actual endpoints 0 to 2 for x, 0 to 1 for y, and 0 to 3 for z. So let's go ahead and start off with let's do dz, dy, dx. So dx is on the outside, y is in the middle, and z is the inside. So 0 to 3 of our function x, y plus z squared, dz, dy, dx. All right, so let's go ahead and integrate with respect to z. And so we're going to get x, y, z, brackets, plus 1/3 z cubed and we're going from 3 to 0. And I'm just going to write this out. 0 to 2, 0 to 1, 3xy plus 3 cubed is 27 over 3 is 9. Dx dy. Nope, dy dx. Erase that because it's not really calibrated. Dx dy. Alright. Now let's integrate with respect to... I just did it again. Dy dx. Alright, so now integrate from 0 to 2. And now we're going to go from... So we're integrating this with respect to y. So 3 halves xy squared plus 9y from 1 to 0 dx. And I forgot to write that dy dz. Nope, dy dx. I should go right there. All right. And now go ahead and plug in. So plug in 1. This is going to be 3. So integrate from 0 to 2. We're going to have 3 halves x plus 9 dx. And then integrate that. I wrote way too big because I'm doing others as well. Daggone it. I can move this whole thing up a little bit. So let's go ahead and integrate. So it's just going to be x squared, so 3/4 x to the 4th, no, x squared, plus 9x from 0 to 2. And we'll square that, so it looks like 3 plus 18, which is going to be 21. Alright, so I'm going to move all this up. Oops. Just move that up there. Give me some room. Alright, now let's do this another method. Let's go from 0 to... What do we want to do? Let's do 0 to 2, 0 to 3, and 0 to 1, xy plus z squared. So we're going to do, looks like the inside's dy, dz, dx. Alright, so let's go ahead and integrate. So 0 to 2, 0 to 3, integrate with respect to y. So 1/2 xy squared plus yz squared from 0 to 1, dz, dx. And we're going to get 0 to 2, 0 to 3. Looks like we're just going to have 1/2 x plus z squared. Dz, dx. Alright, let's do it with integrate with respect to z. So we're going to have 1/2 xz plus 1/3 z cubed from 3 to 0 dx. 0 to 2. And then we're going to have plug in 3, so 3/2 x. Plus 3 cubed is 27, so plus 9 dx, and then we'll integrate one last time. So we get 3/4 x squared plus 9x. 0 to 2, and we're going to get 21 again. Alright, and then lastly, let's do it again. Go from 0 to 1 this time. Zero to 1, 0 to 3, and then 0 to 2. We'll start off with x inside. So we have xy plus z squared. I don't know why I use the closed brackets. Dx, dz, dy. Alright, so 0 to 1, 0 to 3, 1/2 x squared y plus xz squared, 0 to 2, what's next, dz dy, let's clean that up, 0 to 1, 0 to 3, plug in 2, 4 to 2y plus 2z squared, dz dy. Alright, integrate with now respect to z. So 2yz plus 2/3 z cubed from 0 to 3. And that's going to give us the integral from 0 to 1. Looks like 6y plus 27 over 3 is 9 times 2 is 18. Nope, that's not. Make sure to check that real quick. 2y plus 2z squared is good. 2yz plus 2/3 z cubed is good. And then, so 6y plus 18. Yeah, don't want to forget my dy, and then last, integrate with respect to y, so y squared, so divide by 2, so 3y squared, plus 18y, 10, yeah, that's going to give me that 21. All right, and that's it.